Hi, I'm Ahmed Moti from the Sorbonne University and Saint-Antoine Hospital in Paris, in France. And it is my great pleasure to welcome you to this new activity by the IACH. In a letter to Robert Hooke in 1675, Isaac Newton made his most famous statement: "If I've seen further, it is by standing on the shoulders of giants." So, standing on the shoulders of the giants initiative by the IACH, the International Academy for Clinical Hematology, aims to celebrate the achievements of leading experts whose research has helped to significantly advance the field of clinical hematology and establish the milestones and foundations of modern clinical hematology. Our honoree for today is Dr. Narla Mohandas. Dr. Narla is a distinguished scientist at the New York Blood Center Enterprises with a career spanning more than 50 years. He served as an associate editor of the journal Blood for 10 years. Most recently, he received the 2020 Wallace Coulter Award for Lifetime Achievement in Hematology for his significant contributions to the field. Dr. Narla is also currently serving as a member of the Advisory Council of the National Heart, Lung, and Blood Institute, NHLBI. Dr. Narla has made significant contributions to research focused on the pathophysiology of inherited and acquired red blood cell disorders, and his research interests include hereditary spherocytosis, sickle cell disease, thalassemias, and malaria. He also specializes in erythropoiesis with an emphasis on ineffective erythropoiesis in myelodysplasia and Diamond-Blackfan anemia. So you can see really an incredible career and amazing achievements. Dr. Narla, good morning.
Good morning.
How are you?
Very good. Thanks for the very kind invitation, because I feel a little intimidated because some of the people we had before are contributed so much more than me, but I'll do my best to articulate what I've accomplished so far.
No, we are very proud and honored having you with us, and you absolutely deserve being featured in this series. So I always start about the early childhood and early education experience. So, Dr. Narla, and you allowed me to call you Mohan, can you tell us something about your early childhood and early educational experience and how that might have played a role in your selection of your future career and scientific field?
Very much. Thank you very much. I was born in Madras, India. It's now called Chennai. And I did all my initial education there, both in high school and university. And I was always, for some reason, people ask me, when did you get interested in science? I vividly remember I wanted to be a scientist when I was 5 or 6 years old. And I think the reason for that was my father was a journalist, and he was very much wanted to convey science to the general public, and he used to talk about it a lot. So, and the reason I felt I wanted to be a scientist is because scientists always discover new things. And to me, it was a very appealing concept. That is, you can actually make a small contribution to generate new knowledge. So that was my primary goal when I was very young. But then I was not that much interested in biology. I was mostly interested in mathematics and physics because I thought biology was a very descriptive science at the time. This was in early 50s and stuff like that. Whereas I thought physics and mathematics were more challenging in terms of conceptual development. And so in India at that time, as you can imagine, we had only two options, in career. One is to be a physician or an engineer. Both are only those two careers gave you an opportunity to make a living. If you're any other thing, it was very hard. Things have changed obviously over the number of years, and for some reason, biology didn't appeal to me. So I wanted to do engineering, and I started my career as an engineer in India, and I got my bachelor's degree and master's degree in chemical engineering. And I have five sisters and two brothers. They all went to medical school. I'm the black sheep of the family, not having pursued medical career. And so basically, I got my PhD. Then I decided I should go to America to get my doctoral degree in engineering at Washington University in St. Louis. And when I went there, I really wanted to do something new. And biomedical engineering was just starting in late 60s because there's a big interest by the National Heart, Lung, and Blood Institute to develop heart-lung bypass machines and kidney dialysis machines. So they really wanted to encourage research in trying to design these devices that minimize damage to circulating blood cells. So the idea was how can you design pumps as well as biocompatible material that does not damage the blood cells too much. So my project, actually, PhD thesis project, was called red cell deformation and red cell adhesion because because red cells were deformed during flow and they don't want to adhere to the material you're using to make this machine. So that was my PhD thesis. And then what happened was I really wanted, even when I went to America, I said I want to spend my 4 or 5 years getting my PhD and some postdoc, but I always had this fascination of living in Europe for a while to continue my thing before going back to India. So at the time, I was very fortunate at Washington University when Professor Marcel Bessis from Hospital Bisset came to give a talk on red cells. And as you probably are aware, he was a big person in scanning electron microscopy and red cells and hematology in Paris at the time. So I went to him and basically showed him some of the work I did. And I asked him, can I come and spend time in your institute working on red cells? He said, I'll try to do my best, but I'm not sure. I have a full lab right now, but I'll do my best. And I said, thank you very much. And then around a week later or 2 weeks later, he called me at 3 o'clock in the morning in St. Louis and said, Mohan, I said, yes, this is Professor Marcel Bessis. So, oh, I didn't immediately get it because I just woke up. And so I said, oh, Professor Bessis, how are you? And he said, I have a position for you at Institute of Pathology Cellular in Hospital Bisset. And said, you want to come? Without thinking twice, I said yes. The only problem was at the time for me was I didn't speak a word of French. I didn't drink wine and I didn't eat meat. So
But
anyway, I said
today
because
we can state that you are very fluent in French. We have to
not
acknowledge that.
not really. So anyway, but that was to be the reason I'm saying all this is because that changed my life, my career for sure. I would not be what I'm doing today, if I didn't spend those 3 years with Professor Marcel Bessis in Paris, and that started my whole career in hematology. Because when I was at the institute, I was the only non-biologist. Everybody else was biologists. I was the only engineer. And fortunately, it worked out well because me and Marcel Bessis invented a machine called ectocytometer, which was to measure properties of red cells. And that really began my career in hematology in Paris. I'm very grateful to the opportunity to spend that time in France.
Lovely story. And obviously, you mentioned the master Marcel Bessis, and now you have become the master because even the big boss of all the hematologists, because I didn't mention this in my introduction, but you are the current president of the American Society of Hematology. But beside Marcel Bessis, were there any particular teacher, other faculty that you thought at the time to be exemplary of the academic tradition and you could identify yourself or would like to follow their path?
Actually, I will tell you that because I was, as I told you, my background was in engineering and this thing, and I got into Reds. Actually, I tell people I became a hematologist researcher by accident. If I didn't go to Paris, I wouldn't be doing what I'm doing today for sure. I'm sure I would have done something else, but not what I'm doing today. But I must mention very clearly the person who most influenced my whole research career in red cells is Professor Jill Chernier, who was with BICS at the time, but then took over the job as professor of hematology at BICET. And he really, I have a fantastic relationship with him. I tell young people who are PhDs who are getting into biomedical research, if you're doing anything like that, it's very important to learn about the pathophysiology of diseases and work with people, clinicians or clinical scientists who can educate you on what the important problems are in your area of research and use their expertise and combine your expertise with their expertise to develop detailed insights into pathophysiology of diseases. So all the things I've done over the 50 years was really, every part of it was influenced by Professor Jill Chernier. He's the one who led me into studying hereditary spherocytosis, sickle cell disease, Diamond-Blackfan anemia. So at that time, the initial case of, I would say without a doubt, Jill Chernier was really my mentor, and not only mentor, he directed me and pointed me to problems that are of real interest. And obviously, I took it very seriously, and I still work on the same problems after 50 years that I started in Paris here.
So yeah, so your links with France are really very strong, and we're very proud of this. So red blood cell is the key word
Right.
in your career. So what particularly about red blood cell disorders that attracted you to move to this field? Because you said it was maybe by chance, but then we always find the same keyword.
The thing that really attracted me to red cell, because of my background in engineering, and I always thought quantitation is very important. Description is good, but actually measuring something is key to the future of science. So, as you know very well, better than me, red cells are pretty simple cells, relatively compared to all the other cells in the human body, because they're really, some people call it a bag of hemoglobin, which distresses me a great deal. They're not a bag of hemoglobin. They do a lot of things. And as I was even myself surprised after working all these years, when I read a while back that 70% of all cells in humans are red blood cells. 70%. Even my daughter and wife were also in medicine. When I told them, they said, "Oh, no, you're wrong." But I told them to look it up, and it's exactly correct. 70% of all human cells in our body are red cells. More relevant, pertinent to what you asked me was, as an engineer, is a cell you can handle. It's pretty simple. There's no nucleus. It's all plasma membrane is the most dominant thing, and the hemoglobin that carries oxygen within the cell. So, from an engineering and perspective or biophysical perspective, it's easy to study them. Not easy, but at least amenable to much simpler manipulation and stuff like that. So that's what attracted me to that. And people ask me, why didn't you work on platelets or white cells and all? I said, they're too complicated. Red cells are the simplest cell study. But having said that, one of my frustrations in life, in career, is that after spending 50 years, I still don't understand the simple cell. There's still so much more to learn. And sometimes I wake up at night and say, what the hell are you doing? 50 years, you don't understand this cell. So that was a reason for doing that, is really the fact that you have easy access to these cells, relatively easy access to these cells. And once you know what normal is, then you can start studying abnormal red cells and figure out what went wrong with these cells.
So you're highlighting the complexity of these cells and the relevant disorders, even 50 years after you started your research. So in the 70s, 80s, and maybe early 90s,
Right.
what was the status of the research in red blood cell disorders? What were the key questions that attracted you, and you said, "Oh, I need to find a solution for this or this"?
Right. As you know very well, the early part of 50s and 60s, there was a lot of emphasis on nutritional anemias and enzymopathies, G6P deficiency and things like that, with fantastic contributions by Professor Ernest Beutler and Bill Valentine and Professor Bauvin in France. So that was really at the time, those are the two things, nutritional anemia and enzymopathies were attracting a lot of attention. But in 60s, starting 60s and 70s and 80s, there was a lot of interest in red cell membrane disorders. So basically, I was really influenced a lot by Sam Lux at Boston Children's Hospital, who was a leader in red cell membrane research, and David Nathan and Frank Bunn in Boston as well. These people who were actually trained by uh, Castle and Yandel, who are the real leading hematologists at the time at Boston Children's Hospital and Harvard. They actually define how important the spleen is in destroying red cells in various hemolytic membrane disorders such as hereditary spherocytosis. Having said that, I must state right now, hereditary spherocytosis was first described in France in Petit-Salpêtrière in early 1900s, and that is really the classic red cell membrane disorder in our field. And so basically the idea at the time was we knew so little about membranes and membrane architecture, membrane structure, and membrane function. And again, since, as I said earlier, since it's a simple cell, all you do is take red cells, put them in hypotonic solution, lyse them, and spin them down, you get pure red cell membranes. And then it started whole idea. Biochemistry was developing, SDS page gels were developed. So actually, Steck in Chicago ran these membranes in SDS gels and found about 8 or 9 bands on the gel. And these proteins were named band 1, band 2, band 3, band 4, and stuff like that. So just the numbers, we didn't know what it was. And now we know enormous amount of these proteins. These proteins were purified, they were cloned, they're expressed, and things like that. So I can say one thing that has changed since the 70s is that we really have a reasonably good idea of the structural organization of the red cell membrane, all the various components and various how they interact with each other and how they contribute to the flexibility of the red cell membrane and the mechanical stability of the red cell membrane. So that was really a big thing that happened in 70s and 80s in red cell research, is focus on the red cell membrane and the protein architecture of the membrane.
So it looks like it's about a collaboration and cooperation, because you already mentioned several names from different places. So what were the intellectual interactions that took place early in this field? And was everybody aligned on the same objective, or were there different theories and every person was convinced about his or her theory? How did it go?
Really, actually, the one thing I will tell young people who come to talk to me about biomedical research is I've been very fortunate. As I told you, I became a hematologist researcher by accident. The nice thing about the red cell field is everybody is very friendly and cooperative. Really, I really believe that. Even today, there's a lot of camaraderie because we're all interested in understanding how this cell functions. And most of us in the field realize none of us can do everything that needs to be done. The only way to make progress is really working together. All of us have different expertise, really, so really not working together to me is really a shame. And I really find it frankly, quite offensive when people talk about science as a competition and winning and losing. There's nothing to win or lose in science. What you want to do is move the field forward and work with as many. I tell people I really like smart people, to work with, but I also like nice people to work with. Because really, that really enables you to develop long-term relationship with the same passion to solve the same problem that we want to solve. And I've been very fortunate, really, in my life in this regard because I have the opportunity to work with people all over the world. I had 25-year collaboration with people, my friend Yuichi Takakuwa in Japan. As I told you, I've been working with Jill Chernia for 50 years. I worked with Walter Gratzer in King's College in London for 30 years. And I have worked for about 25 years with Dr. Ross Koppel in Australia. And all of these were really not only working relationship, but they became personal friends. We really respect each other a great deal. And I think I tell young people, be very careful that you identify good, smart people and develop a relationship that is sustainable over a long time due to mutual respect, both professionally and personally. That really, to me, is the key to make progress in science. And also, it makes it fun. It really is fun. I really enjoy, even after 50 years, every morning when I go to my lab, I really feel it's a new day. And maybe by chance, I'll find something exciting that day.
Super, super. This is really fantastic. So, speaking about relationship, collaborations, you have trained, I think, dozens of scientists, researchers, PhD students, postdoc, etc. And how did you see yourself playing a role, influencing them in any way, moving towards this field and being passionate about research and science? What is your recipe?
As I said, it's very interesting you ask the question. Number of people come to me, talk to me, young people, saying, I want to work with you. What should I work on? Okay. I said, no, sorry, I'm not going to answer your question. Why don't you go take a long walk and come back in a couple of hours? Okay. And what I want you to do during the walk is to think, what is that fascinates you? What is the problem in this field that you really want to solve? Then come back and I'll help you to make progress in the problem that you're most fascinated, aspect of the problem that you're most fascinated. They said, Dr. Nala, you're so well known and you know everything, so I want you to tell me what to work on. I said, no, I told you I'm not going to do that. And they ask you why. I said, that's because if I ask you to work on a problem and you spend 4 or 5 years of your life working on it and nothing comes out of it, then you'll say, Mohan made me do it. Okay. Whereas if you define the problem and you are successful and you work on it, then you'll be very proud of yourself. And even if it failed, you say, I did my best. And thing. So I'm very clear with my students or trainees that I want them to decide what aspect of the problem that fascinates them. And they're willing to spend 10, 15, 20 years to solve them because none of the problems are trivial or easy to solve. You really have to have almost a lifetime commitment to solve these problems. So that's one thing. First thing I do with my trainees is do that. And the second thing I try very hard is to get them connected to other people in the field who are also very high level of competence and stuff like that because I don't have expertise in everything. As I told you, I never took a class in biology or genetics or molecular biology. It's all learned by working with people who are extremely good. I'll tell you a small anecdote. I was sitting in my office in Berkeley one day, and I get a call from the director of Lawrence Berkeley National Lab and says, his secretary tells me, Dr. Nala, Dr. Shank wants to see you right now. I said, wow, what did you want to see me? Did I do something stupid? Somebody reported me or something. So I was really got into my car and drove up the Berkeley Hills to his office. And I was very nervous, actually. And I walked into the office and he says, oh, Mohan, thanks for coming. I really need your help. I said, I got very relaxed. Like, he needs my help. So he said, sure, Dr. Shank, what do you want me to do? He says, I want you to run the Human Genome Project in Berkeley. I said, what? I'm not a molecular biologist, I don't, I'm an engineer working red cells and hematology. He says, no, no, I worked with you and I know how good you are in managing people and problems. So I really I need an interim director because the director was asked to let go. So I said, I'll try my best. And it lasted 3 years. And on there, I really got to know about human genome sequencing and all the technologies that were derived with it. So I tell people that being at the right place at the right time, uh, and keeping your eyes and ears open and working and listening to good people is critical for whatever you want to do. And other thing I tell young people who work with me is when you have seminars, okay, don't go to seminars in the red cell field. You know, go to every seminar in hematology, okay, because these are given by very nice, smart, well thought out people. So you learn something. It may not be directly relevant to your research problem, but not listening to smart people, how they approach problems and how they solve them is really critical for our development. So that's why when you told me I work on diamond black fine anemia and all, I never imagined I'd work on diamond black fine anemia. Now, more recently in MDS, because they really are not red. No, their anemia is in these things, but they're not real red cell problems. Really, they're more of an erythropoiesis. So after working on the mature red cell for almost 30, 35 years, I decided, what should I do now? How long can I do this? And so I decided at the time, now that I worked on the mature red cell, I would really like to know how this red cell is made from stem cells in the bone marrow. So the whole lab shifted its focus from red cell physiology and pathology to erythropoiesis. And the last, I would say, 10 years or so, I've been focused completely on that. And again, it involved, learning proteomics, RNA sequencing, epigenetics, and all these kinds of things. Because my feeling is if you want to work on a problem, you want to look at it in a bigger picture than a very small aspect of it. Is it not easy? But I think by working with the right people, you can really make significant progress, in my judgment. Yeah.
This is quite incredible to see this transition from, as you said, 50 years ago, started counting the number of cells and now trying to understand the pathophysiology of some of the most complex diseases we're facing in the field. So here, I would be very interested to hear from you about the impact of your research on patients and their families. How do you envision this? Because you mentioned nicely that in the last 10 years, you have switched your focus. And I guess the goal is to go into application to serve and help patients after generating this tremendous body of knowledge over 40 or 50 years.
Actually, I'll tell you, I've been that's always as a basic scientist, and a PhD in engineering. One regret, if you ask me, in my career, would I have done something different? It would be, I wish I had a MD degree. I was not practicing, but enough an MD degree because I think it would have given me an opportunity to really understand the whole physiology and pathology of human diseases. And not just red cells, but in general, the complex biology of the human physiology and pathology. That's the only regret I have. Otherwise, I'm quite happy with what I was able to do. And the reason for that is, I think, as you said, what is important, even as a basic scientist, what I do is how does it impact human health? Okay, you can do all the great studies and all publish great papers, but how does it really impact a patient? Or can you do something to help them? And that really struck to me early on in my career when I was at UC San Francisco in late 70s and early 80s, when I went and visited a sickle cell patient who blood I was studying at the time. She was admitted for a vaso-occlusive crisis, painful crisis. And I saw her almost every day for 6 days. And then as a seventh day, she died. And that really had an incredible impact on my life. Here is a young woman who I was studying her blood, and she was gone. She's no longer there. So that really to me was eye-opening, that we can do all these great measurements and measure this, measure that, and all, but you didn't do a thing for this young lady, to rescue, prevent her from dying. Same thing, when I go to meetings like in Diamond Black Fan anemia meetings and stuff, when you hear the stories from the patient's perspective, huh, what they're going through, I feel very small. I know a lot about diamond black fat anemia and ribosomal defects and all that stuff, but unless you can translate those things, into benefit for the patient, it's really, to me, it's not very satisfying at all. So everything I try to do is really try to work with physicians and clinicians who are taking care of these patients and see how the knowledge I'm generating could be potentially useful, to develop better therapies. So that's one thing I really feel very strong. A little bit of void in my life is how much impact what I've done, has a direct impact on patient care. In that regard, as I've been telling you about sickle cell disease, I've been very flustered. I've been working on it for many, many years, and there's really nothing going on. This is the first human disorder. It was defined molecularly, by Linus Pauling 60, 70 years ago. It was the first molecular disease in humans defined, is sickle cell disease. Here we are, 70 years later, with little to do except one really effective drug, which is hydroxyurea. It really shows you how complex the human biology is, and how it is not that trivial. Just because you know the molecular defect, you can directly translate into improved therapeutic benefits and things. So I really feel very strongly that all of us who are in this doing biomedical research keep that in the back of our mind and not feel very proud that we've defined this defect or that defect, but how does that really impact therapeutic development is important.
No, thank you so much for sharing this. But thanks to the your leadership and the leadership previous leaders of ASH, I think there is more and more awareness now about sickle cell, and we've seen some nice development with gene therapies, allogenic stem cell transplant. But I fully agree with you that the number of patients is quite incredible, a huge number of patients with little access to
Right.
innovation
Right.
so far.
But that's one thing. Other thing, I want to, not only me, but in terms of, I can't speak for Ash, but on my own personal thing is that I really think we really need to worry about the health equities about these new therapies and things like that, because like, for example, very well in some of the malignancies, but in classic hematology, in terms of sickle cell disease and thalassemia and all, these are really diseases of the so-called developing worlds. There are about 100,000 patients with sickle cell disease in North America, whereas there are millions, at least a million or more people around the world, including sub-Saharan Africa and India with sickle cell disease. So if you want to translate this into real effective therapies, it becomes very unequal. Because, like, for example, you talked about gene therapy. The two FDA-approved things for sickle cell therapy. In December, it was announced at the ASH meeting. The FDA approved these therapies, and they cost between $2 to $3 million each, just for the drug, not for the treatment, okay, not for transplant and all that kind of stuff. How many? I don't think even the Western countries, rich countries, can afford to implement these things. So I think, to me, that health inequalities and health disparities are really something we all in our field has to pay a lot of attention to. Otherwise, I think we are not really doing the right thing, in my judgment, anyway. Yeah.
No, but I fully share your concerns, and I can assure you that here at the ICH we are fully aligned because our mantra is about hematology without border, and we advocate for the triple A: availability, accessibility, and affordability. And we need to do a lot about this. Let me switch gears now, Mohan. Uh, and now, if you would like to give a few words about the contribution of your family to this wonderful career, I'm sure they played a role.
Oh, absolutely. I wouldn't be here today without the family support. My wife, Josna, actually, who's a pathologist by training, really uh, shifted my thinking because, as I told you, I invented the ectocytometer with BCs and brought it over to UCSF, and we're studying all these disorders and showing how they're different. And you won't believe this, my first grant, NIH funded grant in late early 70s was titled Red Cell Deformability in Vitro and Survival in Vivo. That was the grant that was funded continuously for 45 years. Okay. So one day I was talking to Josna and she says, you can't spend rest of your life measuring things with hectocentimeter. You better do something else. So it really impacted me a lot. I said, "You're right. How long can I use a technology to advance my career?" So at the time, with my friend Jill Chernia, we found a family in Algeria uh, who are completely deficient in protein 4.1. Actually, it was originally studied at Hospital Cochin, uh, and Jill's patient. They were Jill patients. So because of active cytometry, we got blood from them and studied them. And then I decided to learn something new. I wanted to clone the gene for 14.4.1. So I worked with Y.W. Khan, who was at UCSF with a postdoc, and we cloned the gene for protein 4.1. So that really started my exploration into other things than just biophysics and bioengineering. That is, you really get deep into other aspects of biology and things like that. So if Josna didn't push me into doing something besides measuring the same thing over and over again, I don't think I'd have been as successful as I am, whatever success I had so far. In terms of our children, my son is a Gautam Narla. He's at University of Michigan in Ann Arbor. He's an MD, PhD, and he basically is a human geneticist and mostly focused on cancer genomics and cancer genetics. And our daughter, Anupama Narla, is an MD, and she is a pediatric hematologist at Stanford University in Bay Area. So both of them, I was surprised that both of them went into medicine, but I feel pretty good. Actually, my daughter, Anu, was also interested in diamond black vein anemia as a pediatric disease. So she once sometimes tells me, Dad, I don't think you should be working on it. You'll be my competitor. I said, no, you better take over the field. I don't want to work on it. If you want to work on it, don't worry. I'm not going to compete with you. So, but anyway, the reality is that I think uh, whatever we accomplish, as you know very well, not only our family support is critical. Josna took care of everything while I was traveling, going to Australia and Japan and all doing, and Thailand and all to do research with people or colleagues in those countries. So she played a critical role in bringing the family together and making sure we are all reasonably successful at what we do, things like that. The other thing I would mention is that, as I said, all of my siblings, seven of them are physicians, and I'm the only non-physician in the family. And my father was a journalist, and he really inspired me to read and write, and also when I still remember when Sputnik was launched by in Russia, the first satellite, and went round and round beeping. He was so excited. He gathered all of us around him and explained to us what this impact means for the humanity. So in all aspects of family, I think they have different uh, impact on you, but all of them are important, in your career and your happiness in terms of what you're trying to accomplish. Yeah.
This is so beautiful. I can only say congratulations to the Narla family. One last question, Mohan, and you already alluded to it, but maybe you can give more insight. What are your hopes for the future of hematology, whether classical hematology, malignant hematology, and what kind of advice you would give for the younger generation?
My message would be, it's still the most exciting field. Hematology is still the most exciting field in all of biology and all of medicine, I think. The reason, I mean, don't get me wrong, I think neurobiology is complex and important. But the hematology has a tradition, you know. Actually, people don't realize Anton Leeuwenhoek, the first Dutch microscopist, wrote a letter to Royal Society in late 1600s that using his simple lens, he wrote to this is a quote, when he was greatly disordered, his globules were rigid, but became more flexible as his health returned. You know, so this is amazing to me that it's a single lens. He was I don't know which part of his body he was measuring to look at deformity of red cells, but the fact that he described that 400 years ago to me is mind-boggling. That same thing as I mentioned before with Linus Pauling and sickle cell mutation. I think hematology is the most interesting field in terms of able to apply new technologies readily, to be able to solve problems. So I'm very big proponent of continued involvement in hematology. And I think young people have a lot of opportunity to for example, I know you're interested in myeloma and other diseases, and the amount of progress we make is really incredible, because the technology that are coming out, I tell people the problems is the same. None of us are describing anything new. What we are doing is using new technologies and new thinking to be able to solve them or understand much more deeply than we ever could have understood before. So that's a challenge, and I think that challenge will be there. And young people have a great opportunity to make major contributions. One last thing I would say, really important for me personally, is training young people. I think we need to inspire them. And I'm quite concerned actually that dearth of people going into basic science and hematology and stuff like. So I really feel like, for example, Ash is spending a lot of resources to develop a new talent by we spend about $19 million a year for fellowships to all the way from medical school all the way to uh, junior faculty. Because if you don't fill the void of and not keep the field going, I think we'll all be in big trouble. And I think it'll be a shame because hematology is and will continue to be a leader in breakthrough technologies and breakthrough understanding of biology.
Thank you very much, Mohan. It was really a privilege for me to run this interview with you. I learned a lot about red blood cells. I think everybody has enjoyed your words of wisdom. I do apologize in advance for my ignorance in red blood cells, and maybe I have asked the wrong questions, but I'm sure uh, your guidance, your wisdom is going to be very helpful. So, on behalf of the hematology community, on behalf of the International Academy for Clinical Hematology, I would like to thank you so much for being with us, and a big merci for the giant
Thank you,
Mohandas
Muhammad.
Narla.
I appreciate the opportunity. And also, as I said, I'm a big Francophile. I really have a lot of fantastic hematology friends in France. And I've been doing this for 50 years. I still come many times a year to France to continue my collaborations. And I really am privileged to have got to know you in the last year or two. And I hope to spend a lot more time with you and talk science and about life in the coming months and years. Thank you so much for this very, very kind and generous invitation.
Thank you so much.
Thank
Wish you a
you.
lovely day. Take
Thank
care.
you, sir. Thank you.